are in the process of proving that rational numbers are dense in the reals, meaning that for any two real numbers x and y, where x is less than y, there exists an n element of integers such that x is less than n is less than y. And if you remember last time, I started by showing you that Rudin's proof of this, he skips a big step. He just assumes something that you can't actually assume at all, and we certainly can't assume from what we've learned so far, which is that he got to a point where he had two integers, m2 is less than nx is less than m1, and then, so these were integers, and then he claimed that if this is true, then there exists an m such that m and m minus 1, which are, so they're integers one apart, that nx is between two integers that are just one apart. And this is what he didn't show at all. He just claimed that clearly if there's two integers that are on either side of nx, then there must be ones that are right next to nx on either side. So in order to prove that, what we did in the last video was we proved the well-ordering property of natural numbers, which says that every non-empty subset of n has a minimal element. That's the well-ordering property. It's interesting that this is what's required in order to prove this. Without establishing this, we can't do that. And yet, what I just said, that every subset of n of natural numbers has a minimal element, sounds very far from this, right? So that's what we're going to do today. We're going to we have to prove a couple more little results based on the well-ordering property, and then we'll be in a position to actually prove that rational numbers are dense in the reals. And I just realized I said an integer, but I should have said it's a rational number. There's a rational number between any two real numbers. Okay, so we started with the well-ordering property, and the well-ordering property is not true of the integers. For example, the integers themselves do not have a minimal element, right? Because they can go -1, -2, -3, down to infinity. There's no reason why a set of integers needs to have a minimal element. But the corollary that we're going to show is that for any non-empty subset of the integers, which is bounded from below, does have a minimal element. Okay, so this is something that it's easy to see why this is true if you have a, just by just picturing it, if you have a set of integers, say all the integers with n greater than -5, greater than or equal to -5, you have -5, -4, -3, ... All we have to do is if we add 5 or 6 to each one of these numbers, then it's going to be 1, 2, 3. That makes it a subset of the natural numbers. We know that the natural numbers are well ordered. So the proof is going to be easy to see what it is we have to do. We just need to move the set that we're talking about to the right until it's all above 0. That makes it a subset of the natural numbers, and then we already know that it's true. So Okay, proof. So we're given that S is bounded below. In R. So let Y be a lower bound of S. So we can use the reverse Archimedean property, which is one of those subsidiary Archimedean properties that I proved a couple videos ago, that for any Y in R, we can find an integer that is less than Y. And therefore, if it's less than Y, then it has to bound S below. Bounds S below, because it's even less than Y, and we already know that Y bounds S below. Okay, then we're gonna make another set, B, n minus a plus 1, for all n in S, and that is a subset of the natural numbers. So what this means is, I always have trouble with like these kinds of just simple algebraic manipulations. It always takes me a little bit of time to get it into my head what we're saying here sort of in a natural way. So n are the elements of S. So A, we know, is below everything in n. So if there's a number line from here up, these are all the elements of n. And A is somewhere below it. So if we subtract A minus n, then, or if we subtract n minus A, is going to be greater than 0, because we know that n is bigger, any n is bigger than A, because A is a lower bound of S. And not only that, it's actually outside of S, right? A is not going to be in S because Y is a lower bound and A is strictly less than that. So A is less than the smallest element, than any element in S. So n minus A is going to be greater than 0. So then if we add 1 to it, n minus A plus 1 is going to be greater than 1. So if n minus A plus 1 is bigger than 1, then it has to be a natural number. So this is the set, B is the set of all of these numbers. So B is going to be a subset of n, okay? So what were we just talking about? If B is a subset of n, then B has to have a minimal element. That's the well-ordering property of natural numbers. Every subset of the natural numbers has a minimal element. So B has a minimal element. Let's call that B. So let B, element of B, B, how about that? 3 in a row. Let B, in B, be a minimal of B. So basically what we've done is we've just taken the set S and shifted it so that it's all to the right of 0, so that they're all natural numbers instead of integers, which might be negative also. So the minimum element B has to equal m minus a plus 1 for some m and s, right? Because that's how we defined every element of B is of this form, where m is an element of S, it's m minus a plus 1. So then just moving things over, if this is true, then m equals B plus a minus 1. And m has to be a minimal element of S. Because if we think about it for a second, if there existed another element of S, so say there was an element P of S with P less than M, then there would be an element of B, an an element C where C equals P minus A plus 1. Right? Because this is the form of every element of B. So if P is an element of S, then C here would have to be an element of B. But since P is less than M, C is going to have to be less than B. But we already said that B was the minimal element of B, so this can't be true. So there cannot be a P less than M. Therefore, M equals min S. So that's the last thing we need to know about integers and natural numbers. Now we're ready to actually prove the density of the rationals in the reals. There's one more thing that we need to show then. We need a lemma before we can actually get to the proof. So the lemma is that if we have an x and a y element of R such that y minus x is greater than 1, then there exists an m element of z such that x is less than m is less than y. Okay, so what does this mean? Y minus x greater than 1 means that y and x are more than 1 apart, right? This is the difference between x and y is greater than 1. So they're not close together, they're at least 1 apart. What this says is that if that's the case, if they're farther apart than 1, then there has to be an integer between them. So to prove this, we're going to construct m as the minimal integer strictly greater than x. So we're going to find an m. So we have x here and whatever it is. We're going to find the integer that's the closest to x, that's just past x. Now, this is the thing that Rudin just assumed, because what he had was m here and then m minus 1 here. And then he went on from there to prove the density of the reals. This is the thing that he didn't prove. Everything that we did last video with the well-ordered theorem and what we've done so far today is all necessary in order to make this claim, okay? So we're now going to do that. With what we've done so far, we're going to be able to construct an m. Without what we did so far, we wouldn't be able to do this. So we're going to construct an m, which is just to the right of x, and then we'll have one that's just less than x, and then we can finish the proof. So to do so, let S equal n's element of the integers such that n is greater than x. So we want S to be the set of all the integers that are bigger than x. So S is not empty. We know that there's something in S because of the Archimedean property, because the Archimedean property says that for any y, we can find an n that will make the x bigger than it, right? Oh, no, this goes the other way. We'll be able to find an nx greater. So if x is 1, then we'll be able to find an integer greater than y. That means that there's at least some integer greater than x. So S is not empty. So this means also that if S is all of the integers bigger than x, then x is a lower bound of S, right? But then from what we started by proving in this video, if S is bounded from below, then S has to have a minimal element as well. So call that minimal element. So there's some element of S where, actually I should have just said that m equals the minimal element of S. So there's no element of S smaller than m. That means that m minus 1 is not in S, because if it was, then it would have to be the minimal element of S. So by definition, 1 less than this one is not going to be an S. So if m minus 1 is not an S, that means that m minus 1 is not greater than x. So n minus 1 is less than or equal to x. And that means that if we could just move them over, then m is going to be less than or equal to x plus 1. Now, remember, we started by saying that the very first given, what we're looking at is that there's an x and a y element of R such that y minus x is greater than 1. So if we put all these inequalities together, we have that x is less than m because m is in S, so it has to be less, so x has to be less than m. And then here we have that m is less than or equal to x plus 1. And from the given, we have that x plus 1. In other words, here, if we have that, then we can move the x over and we have that y is greater than x plus 1 or x plus 1 is less than y. So we just showed it. We have x is less than m is less than y. That's what we were trying to prove. Good. So we've shown that if x and y are more than 1 apart, there will be an integer between them. So at this point, once again, we've now shown completely the thing that Rudin didn't say, which is that there exists an integer such that that's just to the right of x and m minus 1 is just to the left of x. We've now shown this, so now we can prove the density. So now, this is the density theorem. If x is an element of R, y is an element of R, and x is less than y, then there exists a p element of the rationals such that x is less than p is less than y. For any two real numbers, there's a rational number in between. So, since x is less than y, we know that y minus x is less than 0, is greater than 0, whoops. Since x is less than y, we know that y minus x is greater than 0. Using the Archimedean property, an integer n greater than 0, so a positive integer such that n times y minus x is greater than 0. It was greater than 1, I'm sorry. What we're doing here is, so we know that this is positive. So if, using the Archimedean property, if this is our y and this is our x, they're both greater than 0. So we can find an n that will make this one greater than 1. So then if you take this and just use the distributive property, we have that ny minus nx is greater than 1. This is what we were just looking at. And so if we have two real numbers that are more than 1 apart, there's going to be an integer in between them. So from the lemma that we just proved, we have that we can obtain an integer m such that nx is less than m is less than ny, right? And now we're almost done. One step. Do you see what we have to do? Now we just divide through by n, and we get that x is less than m over n is less than y. let P equal M over N. And that's it. So we've just found a rational number that's between X and Y. QED. So it's interesting to think about this. We needed two things in order to prove this result, that for any two real numbers, you can find a rational number in between. The first is the well-ordering property of the natural numbers, which is what we've been talking about. But the other thing that's required that we've used over and over is the Archimedean property, which means that without the Archimedean property, we wouldn't be able to prove that there's a rational number between every two real numbers. That's interesting to think about. Does that mean that if the rational numbers didn't have dimension, you wouldn't be able to get them to find one? There would then be two real numbers together that didn't have a rational number in between them? That's an interesting thing to think about.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.